An extremely crude picture of a valence electron in an atom or a molecule treats it as a particle in a one-dimensional box whose length is on the order of the size of the atoms and molecules. So in this question, there are three parts. In part A, for an electron in a one-dimensional box of length 1 angstrom, calculate the separation between the two lowest energy levels. And the energy of a particle in a one-dimensional box is given by this value, where n can be 1, 2, 3, and so on. So here we are asked to compute the separation between the two lowest energy levels. And the two lowest energy levels are E2 and E1. So we need to compute the difference between these two. And that will be 4 8 square over 8m L square minus 8 square over 8m L square. That will be 3 H square over 8m L square. Now here, m is nothing but the mass of the electron. So this is going to be 9 times 10 to the power negative 31 kilogram. And we already know the length of the box, it's 1 angstrom, and the Planck's constant is 6.626 into 10 to the negative 34 joule second. So I'm gonna call this delta E. That's going to be 3 times 1 angstrom is 10 to the negative 10 meters. So if I were to solve this, let me actually just work with everything except for the powers of 10. That will give me 1.829 into 10 to the power negative 68 plus 31 from the denominator plus 20, this 10 and this 10 from the denominator, times joule. The unit of energy is joule, right? So I'm gonna just deal with the other joule, joule second square per kg meter square separately. So I'm going to show that this term is equal to 1. Okay, so let me actually do this here on the side. 1 joule is 1 Newton meter, which is kg meter per second square times meter. So joule second square is going to be this, and this gets cancelled. And joule second squared over kg meter squared is going to be 1. So the units cancel out well there. So once we work out the units, it's going to be 31 plus 20 minus 68. It's going to be negative 17. So the answer is going to be 1.8 times negative 10 to the power negative 17 joule. So this will be the separation of energy levels. Now, moving on to part B, calculate the wavelength of a photon corresponding to a transition between these two levels. So the energy, the delta E, corresponds to the transition of a photon. Transition of a photon, like for these two, between these two energy levels, and the photon has a wavelength, say lambda. So this energy would be equal to hc over lambda, where lambda is the wavelength of the photon. So 6.626 times 10 to the negative 34 joules second. C is the speed of light divided by lambda p. This is what we need to find. And the energy is 1.8 times 10 to the negative 17 joule. So the joule and the joule gets cancelled, second per second gets cancelled. So that implies lambda p is going to be 6.626 into 3 into 10 to the power negative 34 plus 8 meter per 1.8 into 10 to the negative 7. So if I solve this, I'm going to get 6.626 times 3 divided by 1.8. It's gonna give 11.04 times 10 to the, I'm gonna club all the powers of 10 together. That would be 8 minus 34 plus 17 from the denominator. That gives me 9 meter. And 10 to the power 9 meter is nothing but a nanometer, right? So this is going to be 11 nanometer. Now moving on to part C. In what portion of the electromagnetic spectrum is this wavelength? 11 nanometers belongs to the UV portion of the electromagnetic spectrum.